Okay. Welcome to lecture 10 of Rob 101. Today we're going to cover chapter 8 of our book. It's on Euclidean norm, least squares, and linear regression. Let's see. Our learning objectives are we want to learn a way to assign the notion of length or magnitude to a vector. We talked about vector spaces in length in the previous chapter. We want to assign the notion of length and magnitude to a vector. We also want to look into an important problem that comes down to, again, solving a system of linear equations, but when there's no exact solution, and what we can do with that. And that will lead to the least squares problem. And after that, we're going to see an application of least squares for linear regression. So after today, you should be familiar with Euclidean norm, its properties, and how to find an approximate solution for a system of linear equation, no matter how large. And you get to see some familiar examples of using linear systems for some practical applications, such as line fitting and curve fitting. So first, we are going to talk about the Euclidean norm. Suppose we have a vector such as V. It is an n by 1 vector. It's a vector that belongs to Rn. The Euclidean norm of V is denoted with this symbol. We use 1 bar for showing the absolute value of a scalar, right? For norm, we use double bars, and when you write it like this, that's the symbol for norm. Sometimes people put a number here, 2 norm. The Euclidean norm, sometimes also it's called 2 norm. And that 2 is referring to basically this power here. But in any case, we are not adding that 2, but if you see it, it's the same thing. So the norm is defined to be like this. We square each entry of the vector and then sum them up and then take the square root of that. And that will give you the magnitude. Now that's just one definition. You might ask why it's like that. We have many other definitions. This particular definition of norm, there are many other norms you can define. It's called Euclidean norm. Now another way to think about it is that consider V transpose V, okay? V is a vector, it's n by 1, right? So its transpose is 1 by n, right? N by 1. So this will give you a scalar. So what does it look like? Let's say V is V1, V2, right? Just so we can easily write it down. Well, this is just a vector by vector multiplication. We can use our usual standard matrix multiplication, row times the column, right? So it will give us V1 times V1 plus V2 times V2. This will give us V1 squared plus V2 squared. So when you take the transpose of the vector and then multiply it by itself, it actually gives you this form of squaring each entry and then adding them up. And this is actually, going by the definition that we have, this will be a squared version of that norm. You take the square root of it, and that's the norm, or length. Now, if each of the entries were in, let's say, meters, right? When you square them and then add them up, it's in squared meter, right? And then you take the square root, you get the same unit back if this was a physical quantity. Or you can write it in using this notation, using the summation notation, where we're just saying that sum over all entries of the vector. We use the index I, right? I varies from 1 to n. N is the number of entries in the vector. So that's the definition of the Euclidean norm. And this will give you the length of your vector. For example, what's the length of the following vector? It is a, I'm going to use blue, 3 by 1 vector. Tell me so I can write it. By length, I mean the Euclidean norm.
The square root of root 2 squared plus negative 1 squared plus 5 squared? So
correct. So right. We just use the definition, right? We raise each entry to the power of 2 and then add them up, take the square root, and this will give you a number. Now, if you remember, I used to say, like, this is a unit vector. At the time, we didn't have a notion of length. We just intuitively knew that we're moving one unit along one of the axes in 3D. Now, in fact, we can define, using this definition of the length, and check that, well, this is a unit vector because it's Euclidean norm, right? The length is 1 unit. And that's why it's unit vector. So going back to our example, so you add them up, and then you get a positive number. Can this be negative under some circumstances? Why not? Because we're raising every number to, right, power of 2. And even if it's negative, we're doing this, right? We take the whole thing and then multiplying by itself. The negative sign will get canceled. So it's always positive. The notion of length is always positive. Regardless of what direction is pointing, that vector, the magnitude or length, is a positive number. Now, in today's lecture, things are getting approximate when you see this because there are other numbers after dot. I'm dropping them, right? It's not exact. All right, so let's list the properties of the norm. It's not very difficult to verify that the length is always positive. We just talked about it. Now, what does it mean that if the length is 0, the length is 0, the norm is 0, if and only if the vector itself is the 0 vector. All the entries are 0. What's the meaning of this condition?
You can't have a 0-length vector unless it's actually on the origin itself.
That's perfect. So you can't have a 0 length for a vector, right? unless it is actually the vector that starts at the origin and stays there, and that's the 0 vector. Because, again, based on the definition of the vector that we had, right, if any of them is non-zero, it ends up having some non-zero length, so that's just impossible. It's the sum of positive, or it's the sum of non-zero numbers, so the minimum of it is 0.
So is this in any way related to calculating like the hypotenuse of the triangle? Because you're squaring like sides A and B and then taking the square root.
Yes, it's related to that. And that's why it's called Euclidean, right? It's coming from ancient Greeks studying geometry, but this is for any dimension, right?
So if we have like 3 dimensions, doing this would also give that so-called hypotenuse to the third dimension.
Yeah. So the third one, maybe the third property of the norm gives a hint about that. Although it's not directly that. You're talking about triangle, right? And we have A, B, maybe C. C squared is A squared plus B squared, right? Now this is only true if you have right angle here, right? Now we're going to talk about the triangle inequality now. That's the third property, which is a more general case. But if you have the right angle, you do have this property. So the second property of, let's check the chat, we have, all right, we have some answers. Okay. So the second property is saying that if you have a real number alpha, and you multiply your vector by alpha and then take the norm of your vector, you can take the absolute value of that alpha out of the norm, right? You have a vector like V. The norm of V is now alpha times V is alpha times V1 and alpha times V2, right? That was the rule of scalar times vector multiplication. So you have alpha times V1 squared plus alpha times V2 squared. And then you can factor it, right? Now, because norm is non-negative, right? If we would have kept alpha inside, it wouldn't lead to any negative outcome. So to make sure the outcome won't be negative, we put an absolute value, right, for alpha to just make sure if alpha is negative, that won't happen. So this is a very straightforward application of just writing the definition, right? And I made a mistake. This should be alpha squared, right? Thanks. Okay, so sometimes this is called homogeneous property, but you don't need to be worried about the names. This is just a property of the norm. Okay. The last one is called triangle inequality, and this is saying that if you have two vectors, V and W, if you add them up and then take the norm, this is always less than or equal to taking the norm of each vector, individual vectors. Okay? Okay, so let's go over. So actually, your question, you said when there's a triangle, you can just write down the definition of this vector, right? If it's perpendicular, this is one of its, if this is V, this is V1, V2, right? And then it pops out of the definition of the norm. You don't need the third property. But of course, we studied this in the context of usually geometry, maybe trigonometries, right? You can talk about those concepts in vector spaces too. Next chapter, we talk about maybe orthogonality and dot product. We can give more geometric meanings to our vectors. So the first property was that norm is 0 if and only if the vector is 0. The second one was saying that if we multiply our vector by a real number, the absolute value of that number comes out. And that's simply because if you take the square root of alpha squared, it is, in fact, the absolute value of alpha because alpha can be negative, right? And the third property, we're not going to prove it, but intuitively is you can verify it that if I have a vector x and I have a vector y starting from x, continuing that path here, right, and then here. If you take the length of x and length of y and then add them up, or you could add the vectors, right? Because the vectors, if you remember, they carry you from one point to another point. If you're moving to one point and then moving to another point, if you add two vectors, it's the same thing as directly moving to the final destination. You can verify that it gives you the same result. And then if you take the norm of the sum of them, right? This is always the shorter path than traversing them individually by each vector. And the equality is, of course, when x and y are pointing in the same direction. Would make the triangle flat, right? If we had x and then y, then it wouldn't matter. So that's basically, intuitively you can verify it like this, but there are mathematical proof as well. The easiest one uses a Cauchy-Schwarz inequality, which, because we don't talk about it, we are not going through the proof. In any case, what happens if we subtract two vectors? If you have a vector A and then a vector B, right? B minus A is a vector that takes you from the endpoint of A to the endpoint of B. And you can verify that. Just write down two vectors, draw it for yourself. You can verify it. Now, what happens when we write down x minus y? Let's check. Well, all we need to do is to turn y into negative y. If we change y to, y was an arbitrary vector in that triangle inequality. So if we turn y into negative y, so we can have x plus negative y. By definition of the triangle inequalities, it should be less than or equal to norm of x plus norm of negative y. We just talked about it, that if you have a real number multiplied by your vector, the absolute value of that will come out of the norm. So we take the absolute value of negative 1 out, which is, of course, 1. So nothing happens. So it still holds. So that's true, regardless of x plus 1 or x minus 1. So now, this notion of length and metric, you can see, is giving us some inequalities and properties. Sometimes you want to prove something, you want to show something, we use these properties to do that. Now as soon as we constructed this notion of length, now we are equipped with a set of tools that allow us to do different things that was not possible before. Now, the length is taken for granted, but in math is not like that. We have to define it, and there are different notions of length. And we're talking about Euclidean length here. Another example, let's take 3 vectors u, v, w. They are 4-dimensional vectors, and we want to verify the triangle inequality, because we know it's true, so it should hold for any arbitrary vector. First, we calculate the norm of each vector, and that's going to give us some numbers for u, v, and w. Using the definition. Then you can sum them up. You can calculate u plus v. That means add corresponding entries, and that will give you another vector. You can add 3 of them. You can add up 2 of them, v and w, instead of u and v. Now we can check that the norm of u plus v is less than individual norm of u plus individual norm of v, right? So you can numerically verify. It is very useful a lot of time when you see something abstract, try to verify it numerically. And the process of doing that will help you to understand every step of the way, because you have to implement it and verify it numerically. So you cannot miss anything. That's usually very helpful. 3 of them, no problem. You can consider u plus v to be a vector, right? And by extension, then u plus v, norm of u plus v, is obviously less than individual norm of u plus individual norm of v. So you could extend it to 3 terms as well. Okay? Now, do you have questions so far? This is just a very brief introduction to the Euclidean norm. No need to make it more complicated. It's just giving us the length of the vectors and satisfies these 3 properties that we talked about. Now we're going to talk about the fact that many interesting problems in real world unfortunately do not have exact solutions. You're not going to be able to solve a problem exactly. We talked about in length, in details, that if B is linear combination of columns of A, you're going to get a solution. It's exact, it's 0, but it's never going to happen in practice. Okay, so to break the ice for you,
manage and grow
you have to
your
watch
business
ads.
with Wix.com.
Unfortunately.
Your website is the core of your business.
Now this is reality. When B is a linear combination of the columns of A, that's your expectation. She's very funny. She's the queen of shitty robots. She has a lot of dumb robots
Hey,
videos.
Google, turn on the lights.
Watch the rest of it on yourself. So how much are you going to spill the milk? Do you want to minimize it or you want to maximize it? Do you consider the amount of spilled milk to be a cost or error, or is something desired? Emerald says at least it's got some in. That's true, but I think we both agree that the robot could do much better. The spoon was empty. I don't know if you saw that. So I guess we all agree that the robot could do better, and it makes sense to design the system not to do that, to minimize that spillage or some notion of energy or whatever is the cost of the problem that we're going to formulate, right? So we're going to talk about this. Now, it seems abstract, but these are very, very real concepts in problems that we solve. The notion of error, cost, damage, right? Maybe you want to minimize cost as opposed to destroying some material or increasing its lifetime. Maybe it's the amount of money you want to spend building something and so on. Maybe it's a communication channel. The cost is that you want to minimize the amount of information loss, that you're sending signals, right? So it can be anything, and that's the beauty of it. It's very general. All right, so consider our good old linear system A times x equals b. A is n by m, x is m by 1, b is n by 1, same as before. A is a rectangular matrix. Now, we know that if B is not a linear combination of the columns of A, there is no solution. Now, when there is no solution, that means the two sides of the equality are not the same. So if we subtract B from A times X, there's going to be some left over. Whatever that leftover vector is, call it the error. Or sometimes in optimization, people call it residual. Same thing. So the error is the amount of mistake in the solution we have to fail to match two sides of equality. And it is desired to be minimized because in our examples in care fitting, we will see that the right-hand side, these B vectors, are in fact our measurements. And left-hand side, A times X, is in fact our model. It's our hypothesis. It's our imagination of the problem or world. And we would like these two to be close to each other, our model to be close to what we observe in real world. And perfection doesn't exist in real problems. So we settle for minimizing the error. Or we could simply write E. So E of X is just purely to emphasize that this is a function of X for different values of X, right? As a variable, you'll get different values of the error. This is not a constant, right? That's just the subtle notation emphasis here that we use. But both are acceptable. It's understood when you write E that this is E of X. Now, to reiterate, if the system of equations AX equals B has a solution, then it's possible to make the error 0. Otherwise, the error will not be 0. If the error is not 0, then that means the system does not have a solution. Any other ways to find the solution, that's going to be an approximation to the solution, an estimation of the solution, right? So this terminology is very important, not to be confused the approximation or estimated solution, not to be confused with the exact solution of the system. Okay, so getting inspiration from real world and a robot example. It is customary to work with square root of the error, norm of the error. Now, there are many reasons for that. There are historical reasons. There are reasons that in calculus this was just nice to work with. And this least squares problem goes back to Gauss, German mathematician. He formulated that this way. Or Laplace, French mathematician, likewise. But it is widely accepted to write this to the point that nobody asks you questions. I'm just minimizing the square norm of the error. And I tell you that makes a lot of sense. But it's just a tradition. So, based on what we learned so far, I'm going to write down the squared norm of the error. By definition, we know that this is just the sum. This is just a different notation, right? Sum over all entries squared of the error vector. We just learned that this is the same as saying that the error transpose times the error, okay? Now, I can also substitute whatever was the definition of the error inside here, right? The error was a times x minus b. So in fact, what I have is a times x minus b transpose times itself, which is, of course, the norm of ax minus b squared. So we're just substituting the definition of the error inside this term. Now, it gets a little bulky when you look at it, but it's really nothing. It's just an error term, okay? So this is error, error. This is also E. So this is norm squared of the error. Now, based on our previous discussions, we know that norm squared of the error is always greater than 0. At best, when the system has a solution, it will be 0. It is a non-negative value, whatever the value of x. So you can say that it is lower bounded by 0. That's a formal way to say that. That is never going to be less than 0, although it can be equal to 0. So the error is lower bounded by the norm of the error. Precisely here, the norm squared of the error is lower bounded by 0. Now, we talked about norm squared of the error. Now we're going to talk about the least squared error solution. Now,
the question on the previous slide, how do you get from the second to the last, so the transpose and going to the norm squared? Like, what are the squared components?
okay, so the question is, how did I go from here to here?
No, the second to last to the very last. Exactly.
How did I go from here to here?
So you substituted the definition of the error.
So from here to error to the bottom line, I am just substituting the definition of the error. So the question was how I could get these last two equality. So the definition of the error was ax minus b is 0 if there is a solution. And based on our discussion on norm, we know that V transpose V is, in fact, norm of V squared. Okay? Which is the same thing you see here. Because when you multiply the transpose of a vector by itself, in fact, it gives you whatever you see under the square root. So it is a squared version of that. If you take the square root of it, it gives you norm. But generally, V transpose V, or the error transpose error in that example, will give you a norm the squared of the error, right? It follows from the definition of the norm. Okay? But when we substituted the error by ax minus b, it looks a little bulkier, but it's really just the error vector. Does it make sense now? Yeah. Okay. So yeah, so error transpose times error gives you this norm squared because of the property of the norm. Now we say a value of x will give you the least squared error solution if whatever is that x, right, that you can plug it into the equation, out of all possibilities that this squared norm of error can be, right? Out of all possibilities, this becomes the minimum value of that. That makes sense, right? If we're going to settle for an approximate solution, we may as well try to find the best one, the one that minimizes the error. So that's how we're going to define our problem. We call this the least squared error solution, because among all possibilities, the norm squared of the error will obtain the minimum value. Okay? And notice that I'm using this asterisk to show that this is our optimal value, right? And optimality is in the sense of least squared error solution. When people say optimal, you should ask in what sense, because there is no absolute optimality. In the sense of least squared error solution, right? And then when you hear something is suboptimal, that's just the fancy way of saying it's not optimal, because it could be the worst solution. Still, it's suboptimal, right? Unless it's lower bounded, then you have an idea how bad it can get. Yeah?
Why would we need to have like isn't that a scalar?
It is a scalar. So the question is to find the optimal solution, the least squared error solution. Why do we need to take the minimum? Is this a scalar? Yes. The objective is the norm of the error and squared of it. Squared norm of the error. That's the scalar. Norm was length, right? Magnitude, one number. It is a good question, because if this was a vector, what does it mean, take the minimum, right? It seems to be more complicated. So our objectives are giving us a scalar value, right? Now, if such a solution exists, and is unique, you can write it as x star or asterisk is the argmin of your objective function, this squared norm of your, basically, error. Now, these two notations are very general. We're just introducing them, right? In optimization, you see this a lot. So when we say min, we're talking about the minimum of the squared error solution itself. The minimum of this objective function, the error, here. When we say argmin, we mean the argument of that, the variable that we want to solve for, x. So that's the difference between writing min and argmin. This is a standard terminology and way of writing problems like this. Okay? So is everybody clear the difference between min and argmin? Min give you the value of whatever you see here. Whatever you see here after min, right? Squared norm of the error, that's the objective. We want to minimize it. Min takes the minimum value that that objective can obtain over all possible values of x, and the output is that. But the argmin is giving you the variable x that would give you that minimum value that you see here, okay? Okay, this is just a remark on the notation of min and argmin that we talked about. So argmin, again, is the value of x that achieves the minimum of the squared norm of the error. And the minimum, min, is the minimum value of squared approximation error. All right, so now what have we done? We defined our problem. In the context of optimization, defining your problem, you want to minimize some objectives, we've done that. Now we have to solve it. But we are talking about for a particular type of problem, a problem that the error is the difference between a linear system a times x minus b. So this type of problem leads to least squares solution. So least squares solution is for finding the minimum error solution, the solution that gives you the least squared norm answer for linear equations. That's what it does. Now, we're going to assume A transpose A is invertible, which is the same thing as we talked about it last time. What does it mean? A transpose A invertible means columns of A are linearly independent, right? That means the determinant of, that was the pro tip, right? The determinant of A transpose A is not going to end up being 0. And you will see why, because we won't be able to solve the problem. So that's what we assume, and we expect that from the problem setup to be like that. Now, if that's the case, then there's a unique vector x that achieves the minimum, and it satisfies this equation here. So the solution satisfies this equation, and this equation is very famous. It's called the normal equations. We have not built enough tools to talk about why it's called normal equations, but that's what it's called. So A transpose A times X, our solution, equals A transpose B. Now you've seen this before. The only thing we did, we multiplied both sides of A X equals B, right? What I'm doing, I am multiplying both sides from left by A transpose. This is called the normal equations. Now, if A transpose A is invertible, of course we can invert it and solve the problem, which is the same as saying this is the argmin of minimizing that error. And it's the same thing as saying that X, the optimal value of X, satisfies the normal equation. All of these are equivalent. Now, for reasonably large problem, of course, we don't recommend inverting the matrix. We learned matrix factorization, forward and back substitution. That's what we should do.
I'm just a little confused on that middle equation that you have in the box.
Yeah.
Since X star is the minimum but not necessarily the solution, why is it equal? Wouldn't it be like approximately equal to like A transpose B?
It's a very good question. The question is why X star is not the solution, therefore the error is not 0. That means A X star minus B, it is absolutely not 0, unless X star is also the solution. In general, it's not. So why that's the case, that it satisfies the normal equation? Because that's going to be 0 if you subtract both sides. Now, I postponed, that's a very deep question. I postponed the answer to that future lectures when we talk about vector spaces again. But very rough answer to that is that this A transpose that you get on both sides, what it's doing, it is projecting these vectors to a space that you can have a solution now. It is not the same as the original space, right? So there's something that you're missing here, and that missing part is the leftover, the error, and it is orthogonal to, geometrically orthogonal to the solution. Now, I don't expect that to be satisfactory, but it will go beyond the context of this lecture. But yeah, let's remember the question, right? So the question is that if it's not the solution, why does it satisfy the normal equation? That's a very good question. Your intuition says that we are missing something, and where that is it disappearing, or it's somewhere that we can recognize it, where we're missing that. Okay, so now there are two easy ways to show this. One is calculus. That's very easy to show that's the solution. We're not going to talk about that because we assume calculus knowledge. There's an algebraic way to show that. One straightforward way is with completing the square. That's in the book. If you're interested, you can basically read that why the normal equations are the solution. That's the algebraic proof of the normal equations. That's in chapter 8.4.2 of the book, okay? And feel free to ask a question on Piazza about that if you find it confusing. So we defined our problem, And we can actually solve it to find x that minimizes the squared norm of the error. Let's look into some examples. That's already a pretty powerful tool, because the size of the problem can be anything. You can already solve it. So imagine we have this linear system of linear equations. Now we have more equations than unknown. That's usually the case. We have more rows than columns. You can think about each row as an observation. Usually we want to have at least as many as them as the number of columns, the variables, right? It is common in practice to see that we have more rows than columns. For example, if you use a camera in robotics and computer vision to track the motion of your camera, right? Every image is giving you plenty of measurements like this. So every pixel is giving you one row. How many pixels do you have? I don't know, 300,000? How many variables do you want to solve? Well, it turns out that we need 6 degrees of freedom, 3 translation, 3 orientation to solve the problem. So a matrix is going to be 100,000, 300,000 by 6. Right? So a lot more rows than columns in that particular example. In this example, A is 5 by 2. We're after the values of x1 and x2 that minimizes the square norm of the error. Now, the columns of A are linearly independent. It's not very hard to check because one is all ones. The other one is obviously not a factor of that. Now, find if there is a regular solution, and if not, find the least squared solution. First thing we check, we could check in this example with eyes, but we check that the determinant of A transpose A must be non-zero. That checks out. Then we'll calculate A transpose A. That will give us a 2 by 2 matrix because we have 2 columns. Don't forget the right-hand side of the normal equations. If we calculate A transpose times B, which, back to your question on why it's like that, you see that B is 5 by 2, right? But A transpose B is actually 2 by 1, so it's not the same thing. It's clearly is getting mapped to another space. Now, what that space is, we haven't studied that. And that's it. You have the solution. This is 2 by 2, and it's invertible. You can just invert it. It's not a problem. So you have A transpose A inverse times A transpose B, and that will give you the solution. So no need to panic. Very calm. Just apply this solution, and that's it. Now, is this the actual solution, or is this a least squared solution? How can we know?
So like x factor, like the x star factor into the equation actually solve it.
Good idea. One idea from the class is that let's plug it back into the equation and see what we get. If it solves the equation, then obviously it is. Well, we do exactly that. In other words, let's calculate the error. Error should be 0. Well, it is not 0, we already know that if the vector is not 0, the norm of it is not going to end up being 0. Therefore, whether you want to talk about the error, norm of the error, or a squared norm of it, this is a least squared solution. It is not the exact solution of the system. But it is a solution. When you're designing something in engineering, right, this is a solution. We go with this solution. It is the best we can do. Okay, now that we understand least squares and how we can use it to, yeah.
So I wanted to ask, like, in the real world, how does this error arise? Like, what's the source? Why there is an error?
Why, your question is why there is an error in real world?
I mean, or like in, not the real world, but like in that example, why did we get an error?
Because to have an error, B must be the exact linear combination of the columns of A, right? Then you could find actually X that reproduce B, right? Now, when we say that the error is not 0, the norm of the error means that, well, the equation is not satisfied. Two sides are not the same. Therefore, B for this particular X, and we know that there is no better solution. By proof, that's the best. The normal equations will give you the solution if there is one. Now, we know that B is not a linear combination of the columns of A. And the system doesn't have a solution. Okay.
So since it doesn't have a solution, we're just finding the least incorrect solution.
Right, so if B is not the exact linear combination of the columns of A, then there is no solution. That was one of the three conditions for, right? Solutions of the linear system. And if that's the case, the best we can do is to do the least squares. Now, there are other things you can do as well, but this is the standard way of finding a optimal solution. It might make more sense when we talk about linear regression, things just a little more graphics here, right? Not in the violent sense. Okay, we have a table for data, X and Y. These are pairs of points. You can visualize X and Y. You get a bunch of dots in the plane. How can we fit a line to this? Line, straight line, to this data? Serious question. Can we fit a line to these points? Yes? No? Yes? How? No, by that I mean a line that goes through these points. Right. That would be a superpower. We can't do that. So you cannot have a line that goes through all of them. And that's exactly the case of, well, there's no solution, right? If B was a linear combinations of columns of A and blah, blah, that means that, well, these are all satisfied and these points will be perfectly on a line, and that's never going to happen. If you go to physics lab or chemistry lab or whatever you do, your points are all over the place. You're not going to even get a line. We never got a line in all the experiments we did. So, no, you can't do that for the obvious reason that we see here. That's why linear regression is very helpful to give meaning to those concepts. However, we can fit a line approximately. That means a line that captures the trend in data, right? Not necessarily literally goes through them, but it explains the trend, and then we settle for that, and that's usually a good model. It explains the trend in data. So that's what we can do, and that's an approximate solution. The question is, how can we come up with such a line, right? Somebody gives us this data table, or we record it somehow. Okay, now you say, I want to fit a line, linear regression. That's what we're going to learn, right? Least squares, and that's what we use. Now, you already know that a linear model takes this form. You have y equals some slope times x plus y-intercept, right? So let's call y hat to be our approximate values getting from the model. X is the horizontal axis. Y is the vertical axis, okay? So that's the model for a line, for a straight line. Now, well, we have many points. We have 5 points. Now, each of them should give us a line, should satisfy the model that we have for the line, right? So we can write yi equals m times xi plus b. Now we do something smart, and then we separate noun and unknown. Xi, and this constant, this is for b, right? We know them. This is a table. This is data. It's given. Whereas m and b, these are coefficients. These are unknown. We don't know their value, and we want to solve for them. We separate them, and that gives us a vector, a row vector times a column vector of unknown. So we get a row per row of that data table. And we have n of them, here 5 of them. So the next thing, we're going to stack them in a matrix form. So each row of what we just built here, we stack them. Now, m and b, they're not going to change because they are the same for every line. So we get a vector of y, and in this example, we get n rows and 2 columns, right? And 2 by 1. So this is pretty cool because no matter how many data points you have, you can just stack them and use them. More data will make it just better, assuming they're not corrupted and they're not outliers and all of that. So if you have more data, you can use it. You just stack it into this matrix. And we call this matrix capital phi or phi. Let's call the parameters we solve for alpha. So y, phi, and alpha. So we just converted our model line and our data into a matrix equation in the form of y equals phi times alpha. Y is the vector of y data in that table. You can think about them as measurements or observations, right? In practice, these are your observations. In robotics or in a lot of engineering, these are literally measurements coming from your sensor, right? This can be from your sensor. Maybe it's a temperature sensor, maybe it's a pressure sensor, whatever it is. Phi is called the regressor matrix. There are different names for it. In linear algebra, it's called regressor, but it's in the statistics and machine learning, they took that terminology. They might call it design matrix or data matrix. They mean the same thing. So phi is the regressor matrix. And alpha is the vector of unknown coefficients. That's what we are going to solve for. Because if we know alpha, we have the line. right? If we know alpha, we know m and b, we can draw the line. And we can know the value of the line at any point. Now, the beauty of this regression is that now I have a bunch of points, right? Once I fit a model, what is the value, what is the output at this point, right? We don't have it in data table, but I can query from the line that I fit, then I go with this value. Now, of course, that doesn't mean this is perfectly what the value would be in reality, but that's just what the model is describing. So a model is a hypothesis. The reality doesn't care, of course, what's our model. This is our best judgment to pick a good model for that problem. And we collect data from reality to estimate the parameters of our model. So we don't fit our hypothesis to be, we fit data, right, from real world to our hypothesis, the model, to get a model that will explain that. That's what we do. Okay, so we have y, we have phi, we have alpha. What should we do? Well, we know that this is a linear system of equations. From the look of it, from the plot, we already know that there is no exact solution here. Let's define the error for each row, and then we stack them, and then we have our vector of error, which is the same as saying the error is y minus phi times alpha, right? What would be the natural next step? I have a model, it is linear. I can define the error, and I am after solving the approximate solution to this system of equations. Now, the first thing should come to your mind is that, well, I know least squares. That will give me a way to find the answer. So the total error is the squared norm of the error. We can call this total error. We are going to minimize it. And just following what we learned in least squares, it is a fact that we will get as a solution phi transpose times phi inverse times phi transpose times y. Or these are those three equivalent solutions that we had. Or you can say that alpha star is the argmin of squared norm of the error. Or you can say that the alpha star should satisfy the normal equation. That's my solution. If the system is larger scale, we're not going to invert it explicitly, right? Again, factorization, forward-back substitution. So the solution to linear regression, fitting a line to data, is actually coming out of a least squares problem. Now, this is very general and it's true. You might ask, you didn't ask, but I'm going to put it forward as if you asked. One of you might stand up and saying, why line, right? Who cares about a line? I want a curve that goes through all the points. Can we do that? Sure we can. But should we do that? Can you? Now, a line is not everything. That's a very simple model. Can you have a curve that exactly goes through? Now, I draw it a little bad, but the curve is not going backward. maybe like this. Now, you will see in the machine learning course that they talk about regression in very detailed lectures. Starts from linear regression. You can fit a polynomial. You need to choose the degree of the polynomial, right? If you want to, based on the number of points you have, you can choose the degree of polynomial, and you can go through all the curves, and that's called overfitting, right? When you hear overfitting in machine learning, they mean that it goes through all the points. And that's not good because you are overfitting to data, and you're missing on the trend. Was there a simple model that could explain this instead of just making it super complicated and going through all the observation to exactly matching them, right? Yeah, that goes back to the generalization problem. If you overfit, you're not going to generalize, because as soon as you see a new example, you are not going to be able to explain it because you are too, basically the model, not you, too narrow. The model is too narrow-minded to just whatever is in data, especially if the example is novel and it's outside of your training set. But this table, you can call it training set. Okay, so another question they will after is that, can I search in the class of functions to find a function that will give me that trend instead of searching for the best degree of polynomial? That's very cumbersome, right? And that's your project 2. I will talk about it next week. You will do that in project 2. You will change the basis, and you will do that.
So in the context of machine learning, would like loss functions be interchangeable with like error functions?
Yes, the loss function is exactly this squared norm of the error. You can call it objective function, you can call it loss function, you can call it, now if you're maximizing, you call it reward function. The negative of reward is cost. They're all the same thing, right? So there are a lot of jargon, but once you pass these fancy terms, that's what you see here, right? So it's a little more than that, but we see a little bit of it in project 2. You will do the regression for fitting surface to precipitation data. And in the end of the course, we will also talk about classifiers. But they are all related to this context of regression, and very much related to least squares. Now, why line? But just to make it a little bit harder, right, than the previous case, to show that our framework is general, it is not tied to that particular line model. How about you fit a function here to these points, right? Now, I'm going to tell you that this is a quadratic model. You wouldn't know that. If I just tell you data, you maybe make your best guess. Maybe go with quadratic, but that's, again, you can guess that that's not going to go too far in the realm of challenging problems. Now, I'm going to tell you this is quadratic. Let's do that. We have 9 data points. Now, instead of line, of course, I told you already this is quadratic. Let's write a quadratic polynomial. So we have a constant term, we have a linear term, and we have x squared term. And each of them, they have a coefficient, right? We do not know what the coefficients are. And we want to estimate them, just like the previous case. How do we want to estimate them? Using the least squared norm solution. That's how we want to estimate them. Why we estimate them? Because it's not the exact solution, right? So now the terminology probably hopefully makes sense to you. When we say this is an estimation, that means that it's not exact. There is an error. So we do our thing of separating them, known and unknown. Now you might have recognized that this time 1 is in the beginning. Last time it was in the end. It doesn't matter. You can reorder the columns, right? That's not important. This is our quadratic model. Now, you might think this is nonlinear because it's a curve. But fun fact, this is linear. It is nonlinear in x, because you have x squared. But it is linear in the coefficients, and that's what we care about. We know the value of x. We can just evaluate x squared, right? In that matrix that we had. We can just, for each row, we can evaluate x and x squared. That's just going to give us some numbers. What we don't know and we care about are the coefficients, and the model is linear in coefficients. Therefore, it is still a linear regression problem, and it ends up being a linear system of equations. Which makes it very powerful. Now, you're not fitting a line or plane. You are fitting a curve. It is nonlinear. But the model linear, again, linear in coefficient. So define our model y hat, right? For every yi, the measurement, we have xi, and we can evaluate the model. Define the error to be the difference between the model and observed values in the table. Observed values are yi. Y hat y is what you get from the model. You remember last time was mxi plus b, right? It's the same thing. Observations minus the model. Now we have the total squared error, which is the norm, the square of the error. And what we want to do now, we want to solve the problem. We formulated the problem successfully. After putting it in a matrix form, of course. So we have to write down y, phi, and alpha, right? Notice that now phi has another column, and those are x squared. But again, because you know the values of x squared is just going to be a number. That's your data matrix or regressor, right? So we got our linear model, linear in coefficients, y equals phi times alpha. Let's check if phi transpose phi is invertible. That's important, right? Otherwise, we will be in trouble. We're safe. The determinant is non-zero. And I'm not writing it here, but you already know that your solution is what? Right? So this is going to be phi transpose phi is 3 by 3, right? Because we have 3 variables that we solve for. We have 3 columns. So we could actually fit a quadratic polynomial using the same linear regression model. So it is misleading a little that linear regression is not for fitting a line. You can fit nonlinear models. It is linear in coefficients. And we're going to make this even crazier. We're going to add Gaussian or radial basis functions. These are Gaussian bell-shaped curves. We use them to define the model, and then we want to find the coefficient. That's your project 2, modeling a climate basically quantity over a state map. But we're going to do exactly the same thing we did today. Okay. I'm going to answer this question quickly. Ben is asking, how do you get determinant of phi transpose phi if there is no number? There is a number. Phi, there is no variable in phi. These are all numbers, x1, x2, xn. These are all numbers that we get from this table, right? You see here, x1, x2. So we will plug these values in the matrix, and it's just number. So it's going to give us a regressor matrix that is just numbers, right? So the only unknowns are the coefficients, and we can solve for them, okay? Go through the examples. Let me know if you have other questions. But hopefully you'll get comfortable once you solve a few examples. So that covers chapter 8 on least squares and linear regression. Next time, fortunately or unfortunately, we're going back to vector spaces, part 2. Yay! I can see you're excited. Okay.